Assalamualaikum warahmatullahi wabarakatuh. For today's lecture, we will cover about gas chromatography, which is chapter 3. Now we look at the first slide of the GC. Gas chromatography, it is a common type of chromatography used in analytical chemistry for separating and analyzing compound that can be vaporized without decomposition. So basically, the sample is in the gaseous form, and it can volatile to the environment. So typical uses of GC include testing the purity of a particular substance or separating the different components of a mixture. We can divide the GC into two forms, which are gas solid chromatography, GSC, and gas liquid chromatography. But GSC, which is gas solid chromatography, is not widely used because of the limited number of stationary phase. So GSC principle of separation is by adsorption, and GLC principle is by partition. Right? Now we look at the stationary phase and the mobile phase of the gas chromatography. For the stationary phase, which is the phase that is fixed and not moved, it is a non-volatile liquid. For example, the use of a wax, and it is coated on solid particle or capillary tube. For mobile phase, the condition must be gases, which is we use an inert gas, for example, helium, nitrogen, and argon. Sample will vaporize by injection into a heated system, eluted through a column by inert gases, mobile phases, and detected. So the sample together with the mobile phase will be passed through the column and then will vaporize into a heated system. So basically, GC or gas chromatography, it is vitally important in forensic science to separate substance of analytical interest. So GC is the primary technique for the analysis of fire residues. Okay, for example, in the petroleum product, they use as an accelerant in fire, and the peak patterns from the GC analysis can be used to identify the type of product. For example, gasoline that was employed in the fire. So in terms of the forensic application, the blood and other body fluids, we can analyze it by using GC. Okay, so the bloods and also the other drugs and toxins, we analyze by using GC after suitable extraction process have been carried out. Of course, we need to extract the sample first, and then we analyze it by using gas chromatography. So the use of GC in the detection and quantitation of alcohol in drunk driving cases is widespread, because GC involves the use of a separation column, which is made from a length of glass. So it contains also the silica inside that. And like other forms of chromatography, a mobile phase will flow through the separation column towards a detector. Now we look at the other slide. This is the principle in GC. Look at the first. Sample to be separated is converted into the vapor by injected sample at high temperature to ensure the vaporization. So to be amenable to analysis by GC, the compound must have a relatively high vapor pressure. So many compounds can be analyzed in their native form, while many others need to be chemically derivative to make them sufficiently volatile, less polar, or more thermally stable. So for separation to occur, the GC column must contain a stationary phase, and the stationary phase may be a solid or a liquid. So depending on whether the stationary phase is a solid or liquid at its operating temperature, that's why GC is classified into gas solid chromatography or gas liquid chromatography. So we measure the retention time in GSC based on the differences between the adsorption affinities of the sample component for the surface of an active solid, right? And okay, we look at the next step. Sample is mixed with gases, mobile phases, which is inert gas. Then separation will occur. Components are separated according to their partition coefficient, whereby components which are more soluble in the stationary phase, it will travel slower and will eluted last. And the component which is less soluble in the stationary phase, it will travel faster and will eluted first during the chromatography process. Some criteria for compound to be analyzed by GC, it must be highly volatile and also thermostability, which is stable at high temperature. Okay, the real process during the chromatography, GC, gas chromatography, first a vaporized sample is injected onto the chromatography column. Of course, you need to set the temperature first. Um, so especially the boiling point of the material, the temperature must not exceed the boiling point of the material. First, a vaporized sample is injected into the chromatography column. Second, sample moves through the column through the flow of inert gas, which is mobile phases. In the mobile phase, components of the sample are uniquely drawn to the stationary phase and thus enter this phase at different times, and the parts of the sample are separated within the column. Third, the components are recorded as a sequence of peaks as they leave the column. The peak can then be read and analyzed to determine the exact component of the mixture, and the retention time (TR) is determined by each component reaching the detector at a characteristic time. So we can say that the peak, the amounts of peak we can measure by figure it out on the chromatogram, and the area below the peak is the quantitative or amount of uh, the compound appeared, and we can measure the retention time by each component on the chromatogram. And fourth, we can analyze the peak by the number of components in a sample is determined by the number of peak. The amount of a given component in a sample is determined by the area under the peak, and the identity of component can be determined by the given retention time. These are several examples of GC data. You can see that, for example, in this chromatogram, here in the range of 175 to 200, we can see that there are the free fatty acid contents shown on the analysis graph. So actually, this peak appeared. It is based on the collecting data, and they have the reference sample for each of the peak appeared. So in the detector system, it has its own reference value. So that's why the peak is appeared here. And this one is cholesterol, right? So uh, this one is the cholesterol ester and so on. We can determine the compound based on the retention time. The types of compound based on the retention time. Okay. Different compound will have a different retention times. Alright. These figures show the instrumentation of GC. Okay. First thing here is the carrier gas containing the inert gas, whether helium, nitrogen, and argon. And next, this is the flow controller of the gases. This one is the injector port, whereby we inject the sample through this port. Okay. Sample got by using the microstream. And this one is the column, and this one is column Owen, detector here, and the data recorder system. Okay, in our laboratory, which is at the chemistry lab, we use GLC, which is gas liquid chromatography. So your sample must be in a liquid only. If your sample is in the form of solid, you need to dissolve the sample first and make it become a liquid by dissolving with other solvent or any solvent. So make sure that the solvent and the sample to be dissolved it can retain it is thermostability and highly volatility. Okay, if your sample cannot is non-volatile, so you cannot use gas chromatography. Otherwise, you can use HPLC. Okay, because GC is for sample that is volatile, which is can vaporize to the environment. Okay, proceed with the next slide. Okay, this one is the instrument, the real instrument of GC, and this one is the principle. If the question asks you to draw the instrumentation, draw the principle of GC, so you need to draw this figure, right? So the location or the label of the carrier gas, flow controller, the injector port, the column itself, detector, and the recorder. Now we look at the properties of the carrier gas. Hydrogen, it has better thermal conductivity, but the disadvantages of it reacts with unsaturated compound and inflammable, right? So it is quite dangerous to be used. Nitrogen will reduce sensitivity and is also inexpensive. For helium, it is excellent thermal conductivity, but um, unfortunately, it is very expensive. So the requirement of a carrier gas it must be inertness, suitable for the detector, high purity, easily available, cheap, should not cause the risk of fire, and should give best column performance. Next, we proceed with the flow regulator or flow controller of the gas. It is also known as flow meter. The function of the flow meter is to deliver the gas with uniform pressure or flow rate. The flow meters is divided into rotameter and also soap bubble flow meter. For rotameter, as displayed in this figure, it is placed before the column inlet. It has a glass tube with a float held on to a spring. The level of the float is determined by the flow rate of carrier gas. And this one is the soap bubble meter. Similar to the rotameter, and instead of a float, soap bubble form indicates the flow rate. So the gases can be introduced into the column by both devices. Liquid can be injected through loop or septum devices. Okay, this one is the stringless injector, injection port, and the red one is the sample, and this one is the volatile image, which is spread inside the injection system containing the carrier gas flow, and this one is the capillary column. Okay, for column is an important part of gas chromatography. It is made of a glass or stainless steel. So the glass column has an inert and highly fragile. We have two types of column. It is a packed column and the other one called as a look at the properties of packed column. This figure of a packed column is illustrated here. Packed column are available in packed manner. It has higher sample capacity made by metal or glass, which is stainless steel. The stationary phase for gas liquid chromatography for packed column is EEG, ester amide hydrocarbon polysiloxane. Packed column less commonly used. It has an internal diameter 2 to 4 mm, length 1 to 2. This column is densely packed with uniform, finely divided solid support coated with thin layers of liquid stationary phase and accommodate larger sample. Okay, so the advantages, it can accommodate large sample and ease and convenience of